Hello, everybody. Welcome back to class. First class of the week. You survived the test, it looks like. A lot of them looked pretty good. So let me know who's in the chat. And then about in a minute or so, we could get started with our new material. Good morning, Emma. Good to see you. Good morning, Taylor. Ricky, good morning. Good morning, Navik. All right, well, it's 9 o'clock, so we could get started. The way we get started is with the simultaneous sip. So if anybody has coffee or water and wants to join, Zach Davidson, good to see you. Welcome to Linear Algebra. Join in on the simultaneous sip. All right, feel free to write in the chat if you joined in on the sip or if you or any of your family members joined in. Okay. Navik has an emoji prepared. That's excellent. Okay, so we're going to start chapter 6 today, and this will likely be our last chapter. I know we have in the syllabus that we're going to be going through parts of chapter 7, but I don't know. We'll see how it goes. We could go slow. No sister for the sip. Very sad. We'll start with chapter 6. We'll try to go slow. So slow me down if we're going too fast. But yeah, if we end up having time at the end of the semester, then maybe we could do a little bit of chapter 7, but it's not necessary. All right, so this is chapter 6. Which is orthogonality and least squares. Okay, and so we're going to start with section 6.1, which is the inner product length and orthogonality. Okay, so before we get started, just show of hands in the chat. Who has taken, is this, and also just let me know, is this in focus? It looks a little out of focus to me. Let's see if I can adjust this a little bit. It's also a mirror, so I can't see if it looks right. So who has taken Calc 3? Can I just see in the chat? And the reason why I ask is what we're going to be doing today, you do at the beginning of Calc 3. We're going to be talking about the dot product and what it means for vectors to be perpendicular to each other and how to compute the length of a vector. Okay, so if you've taken Calc 3, this should be a little bit of a review, but I'm going to assume no knowledge. So we're going to start from the basics and work our way up. But yeah, so a lot of the notation should be similar and the computation should be exactly the same. Okay, good. So it seems like a few of you have, which is good. But if you haven't, it's not an issue. Okay, so we'll start with the definition. So we have two vectors living in the same space, Rn. So the definition is the number that you get when you multiply U transpose by V, and this will not be our normal notation, but we'll start with this. The number U transpose V is called the inner product of U and V. And it's also written, and it's often written as U dot V. Okay, so you may hear the term, instead of inner product, you may hear the word dot product. They're talking about the same exact thing, and it's just U dot V. Okay, so the way we compute it, so U dot V, well, it's U transpose times V. The transpose of a column is just the row matrix. And when we actually do this multiplication out, we get U1 times V1 plus U2 V2 plus all the way up to UN VN. Okay, so before we get to an example, the dot product, it's an operation. It takes two vectors and it outputs a number. Okay, so this is just a number. And so let's take a look at an example. So we want to compute U dot V and also V dot U. And U is the vector 2, -5, -1. And V is the vector 3, 2, -3. Okay, so I'll give, let's say, a half minute or so to try to work out this calculation. And then we can, if you have an answer, feel free to share it in the comments. But I'll go through all the steps. Yeah, good. A few people are saying -1, and that actually turns out to be the right answer. So let's see how to do this. So U dot V. I mean, and you can clearly see that this is going to be a commutative operation. Dr. Y is in the chat. She says, this is awesome because it's like Calc 3. Yeah, so Dr. Y, if any of your students are also in my class, I expect them to be the stars of this unit. So U dot V, right, we just go through 2 times 3 plus -5 times 2 plus -1 times -3. And we just add these up. All right, 6 minus 10 plus 3 is equal to -1. Okay, so u dot v is equal to -1, and just for the just to complete the problem, we'll do v dot u, but you'll quickly see that they're the same. V dot u would be 3 times 2 plus 2 times -5 plus -3 times -1, which again is 6 minus 10 plus 3, which is -1. Okay, so again, this dot product inputs two vectors and it outputs a number. And we'll see that this number actually has a little bit of importance to it. It's not just some random operation we decided to study. I know it's been a while since we've had one of these lists, but before we get to some more complicated examples, let's write down a theorem that has some of the basic properties of the dot product. And again, if you have any questions along the way, it takes a little bit of time for it to get to me, but feel free to just ask and I'll pause and answer it. Okay, so the theorem so we'll let u, v, and w be vectors in Rn. And we'll let c be a scalar. Okay, so the theorem, it has 4 parts. This should hopefully look familiar to lists that we had in the past. All right, so A is that the dot product is a commutative operation. So u dotted with v is equal to v dotted with u. All right, this should be immediate from its expansion here. If you just switch the orders of u's and v's all the way through, nothing should change with our value. Next, if you add 2 vectors, u and v, and then dot it with w, you could distribute the dot product through. Okay, so u plus v dotted with w is u dot w plus v dot w. Again, like if we just worked with the definition, this would be immediately obvious to prove. C says if we have a scalar times u and we dot it with v, that's the same thing as a scalar times their dot product, which is the same thing as u dotted with the scalar times v. Okay, so part C says the scalar could go wherever we want. It's not going to affect the value of this dot product. And then the last part is probably the most interesting one, is if you dot a vector with itself, you get something greater than or equal to 0. And in fact, the only way you get 0 So the only way you could get this dot product to be 0 is if our vector was 0 to start with. Okay, so this last part says if you take a vector and dot it with yourself, you get a positive number unless the vector you started with was the vector of all zeros. Right, and it shouldn't be terribly surprising because, again, if we were to take a vector and dot it with itself, you'd have u1 squared plus u2 squared all the way up to un squared, you're adding up a bunch of terms that are squared, which those can't be negatives, right? So if you're adding up a bunch of non-negatives, you're going to be left with something that's non-negative. All right, any questions so far? Are we good to move on? Okay. So the definition, we're going to use part D here to find the length of a vector. So the length you may also see the word norm. So the length or norm of V is a non-negative scalar which we denote. It's like picture the absolute value of the absolute value. So that's our norm notation, or the length of the vector. And it's defined by the length of V is equal to, well, this number here, anything dotted with itself is non-negative, so we can take its square root. So the length of V is equal to the square root of V dotted with itself, which, if we work it out, this is just saying it's the square root of V1 squared plus V2 squared plus Vn squared. Okay, so this comes from the distance formula from calculus class, Pythagorean theorem, really. So, and note, if you square the norm of V, you just get V dot V. Okay, so let's just see why this is true in the case. Or let's just see why this is a good definition for the length. In the case where we have a vector in R2, it's nice and easy to draw, so we can take a look at that. So suppose V equals, let's say the vector -3, 4. Find the length of V. Well, here we'd go 3 to the left. Maybe I should draw it in the next panel for a little bit more space. So let's find this using geometry, I guess. Okay, so V would be this vector that points to here. One leg has length 3, right? It's pointing to the left by 3. The other leg has length 4. So the length of the hypotenuse, which is the length of the vector, is equal to the square root of 3 squared plus 4 squared, right? Which is exactly what this formula says up here, which is 5. Okay, so this length definition kind of just generalizes the Pythagorean theorem to a couple more variables. So ask any questions still if you have any. If not, we could just keep going. I know a lot of this is probably review for some of you, but still, it's good to ask questions just to stay on top of the material. Okay, well, let's keep going. A vector, so we're going to be interested in these vectors that have certain length. So a vector whose length is 1 is called a unit vector. And a fact so V is not the zero vector. Okay, then U equals something. We'll fill in the blanks here. I'm going to ask you for some help. Is a unit vector with the same direction as V. Okay, so what scalar do we have to multiply V to? So basically U equals some number times V, right? We want to scale V such that we make it a unit vector. What do we multiply V to make it a unit vector? All right, so the question is, we have some vector V, maybe it's this vector here. This vector is length 5. We want to multiply it by some number such that the new vector that we get has length 1. How do we do that? Yeah, we want to multiply by 1 over the length of V. Okay, so if we have a vector like we have here that has length 5, and we want to find a vector pointing in the same direction, but that's of a unit length, and we're gonna find it's nice and it's helpful to have our vectors all have unit length. Then what we'll do is just divide by its norm. We'll divide by its length. And what you get out is just a new vector pointing in the same direction. It's just shorter. Or maybe it's longer, right? If V was short, like had half length, then we'd be doubling the length. Okay, let's look at an example. Okay, so we have this vector 1, -2, 2, 0. And the question is find a unit vector U in the same direction as V. Okay? So basically, let's try to use this fact. All right, so I'll give you a minute or so to try to work this out. Feel free to put any comments in the chat. If you're not sure how to get started, right, what is this asking us to do? We want to find a unit vector in the same direction as v. Let's just find the length of v and then take our vector and divide by that number. Okay, so we want to find a unit vector u in the same direction as v. You get the vector v divided by 3. Yeah, exactly. So what we want to do is first let's find the length of v, and then we're like basically like that's the entire question. So let's find the length of v, and then we could just write it like this. So the length of v is equal to the square root of v dotted with itself. Okay, and this dot product, so it'd be 1 squared plus -2 squared plus 2 squared plus 0 squared. So it's 1 plus 4 plus 4, which is the square root of 9, which is 3. Okay, so the length of v, this vector living in R4, has length 3. And so u equals 1/3 of v, which we could write, I mean, you could leave it as like this if you'd like. But we could write it as the vector 1/3 minus 2/3, 2/3, 0. Okay, so this vector points in the same exact direction as this vector in 4-dimensional space. It's just its length is 1. Okay, so we say this is the unit vector in the direction of v. Again, please ask any questions if you're unsure of how we did some calculations. I don't know if it's because it's the beginning of the week or what, but the chat's a little bit quiet today. Even if you, let's say you're feeling really good about this material, let me know that. You know, give me a thumbs up, or some of my calc students they like to do the dab emoji if they get it. So, you know, you could do the dab emoji to let me know. Okay, let's do another example. Okay, so let W be the subspace of R2 spanned by X equals 2, 3. Okay. Molly says peace sign. Nice. Okay, so before we even get to, there's more to this question, but just as a reminder, or somebody in the chat, so W is the subspace of R2 spanned by this vector 2/3 1. So x equals 2/3 1. What does W look like? Like what word do we use to describe W? Is it a point? Is it a line? Is it a plane? Is it three-dimensional space? Is it higher than that? That's my question. And while you're answering that, I'll finish writing down the question. So find a unit vector z that is a basis for W. Yeah, it's a line. So this looks like a line. It's a line through the origin, and it points in the direction of 2/3 1. So every 2/3 it goes in the x direction, it goes up 1 in the y. So the question is find a unit vector z that is basis for W. And then the other part of the question is there another solution? Okay, so while you're working this out, I'll draw what W looks like just so you have it in your notes. So W would look like this line here. Every 2/3 you go over in the x, you go up 1 in the y. Okay, so does somebody want to share in the chat how they plan on finding such a unit vector? Or maybe just saying, I don't know if you're not sure, because then I could try to explain some more. Yeah, exactly, Taylor. What we'll do is we'll take x. So, right, W is spanned by x. It's also spanned by any scalar multiple of x. So let's just find the length of x and then divide by it. And that'll give us a unit vector with the same direction. And we could use that to solve the answer. For the length of x, I got square root of 13 over 3. Good. Yeah, so that's right. So let's just work it out now, see if we can catch up with Taylor. So we want to first find the length of x. So it's the square root of the dot product of x with itself, which is the square root of, well, you just square each of the entries and add them together. So 4/9 plus 1. Well, 1 is the same thing as 9/9. So we get the length of x is equal to square root of 13 over the square root of 9, which is 3. Okay, so the answer for the first part of the question, z, could just be 1 over the length of x, so it's 3 over root 13 times the vector 2/3 1, which is the vector 2 over root 13 and 3 over root 13. Okay, right, so what did we do? We just took x and we scaled it, so it's a unit vector now. But the second part of the question is there a second solution? Is there another unit vector that's also a basis for w? Or is there just one? Is this the only unit vector? Is this the only unit vector? So it looks maybe something like this. Is this the only unit vector that spans w? Yeah, we could. We never said that our vector had to point in the exact same direction as x. It could be in the negative. So if we multiply this vector by -1, we get a second. So we'll call this z1. So this is a basis for w, but z2, which is just the negative of z1, also is a basis for w. Right, and so that would look like this. So this is the vector z1. The one in this direction also spans w, also is a unit vector. Yeah, so there's one unit vector that points in the same direction, but there's 2 unit vectors that will have the same span. So is this clear how we got these answers? Feel free to, give me any feedback. So another thing we're going to look at is the distance between 2 vectors. Okay, so if we had 2 vectors, let's say we have 2 vectors here. We want to find their distance. So we want to find the length of this dashed line. Okay, so this is what the length of this dashed line will be what we call the distance between 2 vectors. So the way we get that well, if this was the vector u and this was the vector v, this vector starting at u and ending at v would be the vector v minus u. Okay, so our distance between vectors is just going to be the norm or the length of v minus u. So for vectors u and v and Rn, the distance between u and v, which we write distance between u and v is the length of the vector u minus v, or v minus u. It's just they have the same length, and so it's given by the distance between u and v is equal to the norm of u minus v. Okay, so for example, so I want you to compute the distance between the vectors u equals 7, 1 and v equals 3, 2. So this is really asking how far apart are their endpoints if we were to plot these in R2. So I'll give you a couple of minutes to work this out. Again, please ask questions if you have any. Good, Taylor. Do you want to briefly explain what your process was to get the square root of 17? You don't have to go through all the math, but just what did you compute? Me too. Good, Emma. Yeah, exactly. So we'll take the difference, and it doesn't really matter which order we take. Here, like in my drawing, I had v minus u. Here we have u minus v. We're going to see that they're identical because we're going to be squaring a bunch of terms. So any negative that appeared would vanish anyway. So u minus v is the vector 4, negative 1. And then its length. So the question just says compute the distance, which we said is the length of u minus v. So if you were to plot these 2 points in the xy plane and find their distance using the Pythagorean theorem, you'd get square root of 17 also. So this is just another way to do that. Okay. So I know we're kind of hitting you with a lot of definitions today, but that's what happens in the first section of a chapter. Tends to be a lot of definitions. So let's go with one more definition. And this is like really one of the most important definitions of today. So two vectors U and V in Rn. So they have to both be in the same dimension. This doesn't make sense when they're living in different dimensions. So two vectors U and V in Rn are orthogonal. Another word you may see is perpendicular. So two vectors, U and V in Rn, are orthogonal or perpendicular if their dot product is equal to 0. Okay, and so we'll see by an example that vectors that are orthogonal or perpendicular, vectors that satisfy this property, actually meet at a right angle, like like what we were taught perpendicular meant in elementary school or middle school. All right, so for example, so if U is equal to the vector 3, 1, and V is the vector negative 1, 3, it's not hard to show that their dot product is 0. Right? We have negative 3 plus 3 equals 0. But if we were to graph these in the xy plane, you can see my drawing is not perfect, but you can see it appears that they actually do meet at a right angle. And so we'll see with a little bit more detail that this is a good definition. But yeah, so so the way to check to see if two vectors meet at a right angle is we just compute their dot product, and if we get 0, then they meet at a right angle. Okay, so and how do we know these? Well, what's the slope of this line? It goes over 3 up 1, so it's like 1/3. So this line has slope 1/3, and this line has slope negative 3. So those are negative reciprocals of each other. So think back to your Algebra 2 days in high school. That should be perpendicular. Okay. Yeah, that seems like a good place to stop for today. We're going to extend this idea of orthogonal tomorrow to talk about subspaces instead of just vectors. But this is, a good introduction of what we'll be seeing these next few classes. So what do we got? No homework this week. I will give you one though for after starting with the material we cover this week. Make sure you hit the like button before we leave. You know what I'm saying? We gotta get to 1,000 subscribers, and we're not getting there anytime soon, sadly. Yeah, I'll stay around for a few minutes to answer questions, but if not, you're good to go. And the tests, they look pretty good, but we haven't started grading them yet. That is we're going to start doing that this afternoon. So I'm not sure when you'll get the test back, but they'll just be posted to campus. Noah just answered that. Hopefully in a few days, but we'll see. I got to talk to the TA. If he's available today, start cranking them out starting today. All right. Well, if there's no more questions, I will see you tomorrow morning, 9 o'clock. Bye-bye.